Hello and welcome to our tutorial and tour of the PhET Isotope and Atomic Mass online lab simulation. Today you'll be working on the 3B11 Atomic Mass Laboratory. There is the handout that goes along with it. You'll need to put all your answers on this 3B11 handout using Kami. And it tells us to go to Google Classroom and click on the link to the PhET lab. And here's what the PhET lab will look like when you get to it. When you click the link, you'll look like this, right? It'll look just like this. And you will need to open the lab by clicking on the arrow. And you'll wait a second or two as we're waiting right now. This is a great lab, by the way, for understanding isotopes and how the isotopes influence the atomic mass of atoms. And we'll also be getting a little bit more hands-on, if you will, on how to calculate the atomic mass. But here we go. You'll come to this page right here, isotopes and atomic mass. We'll use the mixture portion of this, the last part of the lab. But we'll start with the isotope portion first. First, we click on this. You'll want to click the positive sign right here so that you can see the nuclear symbol. And you'll want to click the abundance in nature so that you can see the percentages of each of the isotopes in nature. Immediately, it'll take you to hydrogen 1 isotope, the simplest of all atoms. Hydrogen 1 is merely a proton with an electron flying around it. And what you're going to do is begin recording that information about hydrogen 1 on our table on the laboratory. So in part 1 of the lab, we're going to be building hydrogen's isotopes. The first one we built, hydrogen 1. That was the one that was built for you when you clicked on the lab. You'll fill out the particles, protons, neutrons, and electrons. That is right up here in the upper left-hand corner. Protons, neutrons, and electrons. There's 1 proton, no neutrons, and 1 electron for hydrogen 1. That's where we get the 101. Is it stable? It's asking you about the stability. We see the stability right here inside the electron cloud. This blue is meant to be the space that the electrons are orbiting around the atom. This atom is stable. This is the nuclear, or the hyphen notation is right here, hydrogen 1. The nuclear symbol format is right here. Up here in this side, you see which elements we're working with. So right now we are on hydrogen. And then you'll need to know, we'll need to come here. The mass number is 1, but that is given right up here as well. The 1 right here is the mass number. The red 1 is the atomic number. The red 1 corresponds to the number of protons, which are also in red. So you see those two things linked. But we're going to need to write down the abundance in nature number, and we will need to click on the atomic mass. We see it's 1.00783. That will go right here. The 1.00783 goes here. The abundance goes here. And then you will make, you'll fill out the nuclear symbol 1,1 in that portion of the table. There's different ways you can do it. If you just want to copy and paste a picture of the nuclear symbol, you can. Or you can use Kami and type in the numbers, whichever is faster. Then you will build hydrogen 2. Hydrogen 1 had 1 particle in the nucleus, and that particle was a proton. Hydrogen 2, how will we build that? Well, that's why we're doing the lab. They have neutrons right here to add to it. You'll add neutrons right through there, and then you'll see as we add neutrons that all the numbers change. So that'll take us through part 1 of the lab. Then you'll need to do a couple questions about what you did, and then you'll need to show the entire calculation of the atomic mass of hydrogen by plugging in the numbers that you have in the table right up here. It's atomic mass times the abundance. So in that first bracket underneath hydrogen 1, you'll put the atomic mass, 1.00783, and then you'll write the abundance. But remember, we've got to take it out of percent form by sliding the decimal 2 to the left. We would get 0.9998885. That would go right here. And then you'll do the same for hydrogen 2. In the second part of the lab, you're going to build lithium's isotopes. However, you start with lithium 7, and then you have to get to lithium 6. Figure out how to do figure out how to go from lithium-7 to lithium-6 using the simulation. Then build some of the other isotopes to see if they even exist. Then you'll calculate the atomic mass of lithium atom, which is sometimes called the average atomic mass, because you're going to average a weighted average of lithium-7 times lithium-6. Then you're going to take a look at some other atoms here. We're going to look at, on this portion of the lab, they're going to give you the abundance of some of the different isotopes. You have to figure out what the isotope is. So when you're doing this part, for instance, for beryllium, when we're doing this part, you'll come up here and you'll click on beryllium. It looks like beryllium-9 has 100% of the abundance. So you would come back to the table. Write the hyphen notation. Beryllium-9 is 100%. You'll write the atomic mass and the stability, and then you'll write the nuclear symbol, which again is right here. There's your abundance, and there's the atomic mass. Then you'll have to play with some of the other isotopes to find out which one is available in trace amounts. So you'll build different isotopes and see which one's trace. You'll do the same for carbon. You'll do the same for oxygen. On part 4 of the lab, you select boron or nitrogen. You get your pick here, and you'll put the different isotopes that exist for either boron or nitrogen. There's 2 rows to the table, so I'm guessing that there's 2 isotopes for boron and nitrogen. You'll fill out the table, and then for whichever one you did, if you did boron, you would write atomic mass, and you would put the letter B right here, and then you would put which isotopes you had, boron whatever, above the brackets, and plug the numbers in here. Part 5, you're going to build neon, and you're going to build neon's isotopes. So on our simulator, you would click on neon, and you would go to work, building the different isotopes. Neon 20 must be one of them. As we see right there, neon 20 is one of them, and then you need to build 21 and 22. Fill out the table, calculate the atomic mass of neon. We're doing this because earlier in one of our first calculations for atomic mass, we did neon. And what we want to do is do neon again to see on problem 10 from 3B10, we did some rounding of the numbers. We didn't use all the information, and it's fun to see what happens to the atomic mass when we have better numbers to work with. Then we go to part 6. In part 6, there's 2 other ones where helium and fluorine, those are 2 of the other symbols on the periodic table that we didn't mess with their isotopes. You need to build the isotope that is 99.9999% abundant, and then build the one, the 0.0001% isotope. You'll do the same for fluorine. You'll build a couple of the fluorine's isotopes and fill out the table. And then we go to the other part. We're going to go to the mixture part of the simulation. So we'll come back here on the simulation. And if you click right down here at the very bottom, click on the mixture, and it'll take you to the mixture portion of the simulation. And you can look on this part of the simulation, you're going to be seeing how the abundance of the different isotopes can impact the average atomic mass for that atom. So you will have an opportunity to see what the actual, in nature, what the percent compositions are for hydrogen 1. It would be 99.9885%. Hydrogen 2 is abundant, is 0.0115%. We can see that. There's the one green, represented by green. There's the one green hydrogen 2. The rest of these are hydrogen 1. And you can get a feel for what they mean when they say 0.0115% abundant. Then they show you what the actual atomic mass is. So with this part of the lab, this is fun to play with, where you can actually see what the percents would look like. In this lab in particular, we're going to be working, if you look at your lab report, there's going to be several questions about what the mixes are. And when they say mixes, they're talking about the abundance of the different isotopes. And we're going to be working mostly with the boron 10 and boron 11. So on boron 10, boron 11, you can see what the actual mix is. And then you are going to build like your own. You're going to click on My Mix and follow the directions where it tells you what orders to put these in so that you can see where the actual numbers are coming from in nature. So that's what this is just getting you a chance to see how the ratios of the boron 10 to boron 11 influence the actual atomic mass or the average atomic mass of the boron atom. This pie chart is showing you the percent compositions broken down for the different isotopes of boron. If you just follow the directions here on this part of the lab, directions are right here for part 7. It tells you what to do. It tells you how to do it. Right here, you're going to start with one boron 10 atom. Then you're going to add another boron 10 atom to your mix. And then you're going to add, it looks like, 8 boron 11s. On this row right here, you're writing the percent of boron in the mix and the percent of boron 11 in the mix. Percent of boron 10 and percent of boron 11. So this is already filled out. The first column's for you. When you put one boron 10 in there, 100% of the atoms are boron 10, 0% are boron 11, because you haven't added any boron 11, and it tells you the atomic mass. On this part of the table, or on this part of the thing, you only need to keep 4 numbers. You only go out to the 100th place on this. Then you add a boron 10 and see what happens to the percents of each in the atomic mass. Then you begin adding boron 11. So you write the numbers down of percent of boron 10, percent of boron 11, and the atomic mass when you've added one boron 11. Where will it tell you those percents? It'll tell you right here. When you're doing My Mix, as you add them, the percents of each will come up. So that's what you're doing. There's one boron 10 in there. So it's 100% boron 10. And there's the mass that's on the table. Then you'll add the second boron 10. Hey, it's still 100% boron 10. Look, the mass is still 10.01294. Then you're going to begin adding boron 11s. Obviously, we now have one boron 11 in the 3 atoms. So it's now 33.3% boron 11. 2 out of 3 are boron 10. 2 divided by 3 is, or times 100, 2 divided by 3 times 100 is 66.7% boron 10. So the percents will be there, but notice the mass changes. Watch what happens to the mass when we add a boron 11. It was at 10.01. We add 1. It goes up to 10.34. So as you start adding boron 11s, watch what happens down here to get the atomic mass. This is how we will be messing with this website here. I highly encourage you to not just do this for boron. You can do other elements as well to see how your mix compares to the actual mix. Feel free to go rogue on this thing since it's a computer simulation. You can kind of create your own investigation as you see fit. But when you finish the 3B11, please compare your work to the answer key that is provided on Google Classroom. Correct your work, compare your work to the answer key to be sure that you're understanding the various concepts that are intended to result from doing this lab simulation. When you've corrected your lab, you'll submit it. There is an additional periodic table, a periodic table we haven't used yet, that is attached to Google Classroom in both the class information section as well as in the Google Classroom assignment for 3B11, because this periodic table that is attached for this goes out to further and further decimal places. It goes well beyond the hundredths place so that you have a better set of numbers to compare to as you're doing your calculations. It's more precise. It just gives you more numbers to look at. As always, if you have any questions on the lab, do not hesitate to ask, and good luck.